All right, so like I mentioned a minute ago, today is going to be a very different day than typical. We're going to go through a lot of factual content, emphasizing the facts, and trying to understand them from an intuitive standpoint, and use Mathematica to do simulation whenever it seems reasonable. So I'm titling this class 13 here, Theory of Estimation Part 1, Point Estimators, Unbiased Estimators, something new, Asymptotically Unbiased Estimators, Variance of an Estimator, Consistency and Efficiency. Just going to try to get as far as we can get. I'm not positive that we'll be able to get to all these topics, but we'll get as far as we can get, and whatever we don't get to today, we'll talk about next Tuesday. I mean, we'll probably talk about it to some degree next Tuesday anyway, but let's review some definitions and facts that we already know. But I'm going to be a little bit more general and use some new notation. So here's our setting. We assume we have a population that's described by a parameter theta. Do this in case I need to do some writing as well here. It's kind of strange to use theta, but it's the standard thing to use for parameters, arbitrary parameters. It's not an angle, maybe except in certain applications, perhaps. More precisely, we have a population random variable. Now, sort of a new way of thinking about populations, though I have mentioned it before. You know, typically when you think about populations in statistics, you are typically imagining, well, populations of literal people or companies or every baseball player who's ever lived statistics. That's what you're usually thinking about when you think about the word population. You want to study the population. But here what we're really doing is we're really thinking about a population random variable. And in doing statistical modeling, quite often you go ahead and you make assumptions about the random variable, like you assume it's normal, or you assume it's gamma with some alpha and some beta. You assume it's Poisson distribution. Sometimes those assumptions are very logical based on the setup of the situation of the model. Sometimes they might seem reasonable. Sometimes they're guesses. Other times we might not have a specific random variable in mind, and we're just after things like estimating the mean. We're pretending the PMF or PDF, depending on whether it's discrete or continuous, depends on theta, and it's standard to write it like this. The subscript capital X is just referring to the random variable X as usual. Usually we don't write we just write a little X in there. We don't write the semicolon and the theta there, but this is just to emphasize that it depends on theta. Now, this is not what I typically do. I typically put the theta as a subscript, the parameter as a subscript when I write families of functions. But in statistics, it's standard to put it after a semicolon inside the function argument. That parameter could be a vector parameter, so it could be like a boldface theta that is really a k-dimensional vector. Most typically, there's one or two parameters, but in general, there could be k parameters. Here's our standard examples, okay, that we've talked about both in probability and statistics and here in applied stats many, many times. Going back to chapter 3, you've got a geometric distribution with probability mass function given by that. Let me just remind you, the typical application is that you are X, the random variable X counts the number of trials until the first success. That's geometric, not binomial. You do have P, a probability of success on each trial, and you assume each trial is independent. You're not counting the number of successes like you do with a binomial. Instead, you're counting the number of trials until the first success. That's geometric. The probability of it taking X trials till the first success is this. Because you've had X minus 1 failures, and the probability of failure on any trial is 1 minus P, by independence, you multiply these things. Mathematica can confirm the PDF. There it is. Mathematica can also find the CDF. And it is described in the book this way. You actually do need the floor function here because remember, these things are really defined for all x. Although it's Mathematica is not doing the greatest overall job here because technically speaking, you need to understand that you use this formula actually only when x is 1, 2, 3, etc. So saying x is greater than or equal to 0 there is not quite right. They're probably thinking about the geometric distribution a little different than we are. They're probably thinking about it in terms of the number of failures before the first success is what I'm guessing here, instead of the number of trials until the first success. Yeah, so they're thinking about it a little differently. So you'd have to be careful here. But we are still assuming this is only defined for integer values of x, by this formula at least. So it's a little imprecise in Mathematica, but here you really can, with the CDF, assume x is any number greater than or equal to 0. Here's a binomial PMF. There we have our standard n choose x times p to the x times 1 minus p to the n minus x. Confirm it with Mathematica. There it is. This stands for the binomial coefficient in Mathematica, n choose x. The CDF adds up the PMF values, and Mathematica writes it in a strange way. Beta regularized. What in the world is that? And that's just a function you've never heard of before. It's a sort of a name for a new kind of function you've never heard of that can represent the sum of things like this. Don't worry about it. It's not a big deal to worry about. By the way, if you're going to plot these things, you'd want to use, at least with the PMF, discrete plot instead of regular plot. We need a particular values of n and p though. 10 trials, probability of success being 0.4. Here's what a discrete plot looks like. Actually, with the CDF, we probably can plot it with a regular plot. I'm guessing. It's going to be a step function. If it does indeed plot it. Yep, there we go. There's the CDF for this discrete random variable. Here's a Poisson. CDF for a Poisson involves gamma regularized. Adding up things like this is a new kind of function related to something called the gamma regularized function, whatever that means. If you want to investigate what it means, you're welcome to. You don't have to. Okay. Uniform distribution. And by the way, in showing you all these things, I forgot to emphasize something important. In each case, you've got parameters. For the geometric distribution, your parameter is p. That's the theta. For binomial distribution, your parameters are n and p. 2 parameters. That's the vector theta. For the Poisson, your parameter is k, which does happen to equal the mean. For a uniform distribution over an arbitrary closed and bounded interval a to b, the parameters are a and b. It's assumed a is less than b. A gamma distribution has parameters alpha and beta. An exponential distribution has parameter beta. Though I did remind you of this before, I'll remind you again, when you do it in Mathematica, for a gamma distribution, you plug in alpha and beta as they are. For an exponential distribution with parameter beta, you actually have to plug it in as 1 over beta to get the right formula. That's because beta is the mean of an exponential, but it's also common to think of an exponential's parameters called lambda, where lambda is related to a Poisson distribution. And then when you write the formula in terms of lambda, it looks like this. The mean, if you think of the parameters being lambdas, then 1 over lambda. Chi-squared distribution has a parameter little gamma, which is the degrees of freedom. Normal distribution has parameters mu and sigma squared, mean and variance. Though in Mathematica, you've got to plug it in the standard deviation instead of the variance. There's its PDF. Here's its CDF, IRFC. It's called the complementary error function. Actually, when mu is 0 and sigma is 1, that's the standard normal. This is the same thing as way back when, 4 weeks ago, we used the capital phi notation for. The CDF of a standard normal. IRFC stands for complementary error function. You can look into details. Student t distribution has this formula. Actually, this is not the formula that you'll see in the book exactly. It's writing the denominator in terms of something called the Euler beta function, B. Our book writes it in terms of the gamma function. The Euler beta function and the gamma function are related to each other. But Mathematica writes it in terms of this Euler beta function. Again, whatever that means, I'm not saying. It's not a big deal. We can just use the technology and not worry about it. Remember talking about the F statistics a little bit in problem stats? A little bit. I haven't talked about it in here, but there is its PDF. In Mathematica, it's called the F ratio distribution. It's got two parameters, M and N, or a two-dimensional vector parameter if you prefer. Anyway, point is all these things can be accessed in Mathematica and they all involve parameters. What is an estimator? We have talked about estimation to some degree. We also talked about method of moments and maximum likelihood estimators. We've already done that. I'll remind you of those things again. But here we're talking more general theory. We have emphasized that an estimator is a statistic. But not just any old statistic. It's a, you might say it's a statistic used for a purpose to estimate some parameter. What is a statistic? It's a random variable that is a function of a random sample. What's a random sample? A random sample is a list of independent random variables from some distribution that all have the same distribution, the same PDF or PMF if it's discrete as some random variable X. And by the way, you may have noticed Mathematica always uses PDF even for PMFs, just like our book does. In the abstract, we write an estimator with a hat, theta hat. It's some function of the random sample. U is some arbitrary function of the random sample. So it's very abstract. Think about examples to help. The mean, sample mean, is an estimator for the population. This expression right here, that is the U function. It's in fact a linear function of the x's, where the coefficient of x each x, if I multiply the 1 over n back through like this, the coefficient of each xi is 1 over n. It's a linear function of the xi's from the random sample. I'm calling it a natural estimator. I could also call it a logical estimator. It just makes sense, right? That's an average. You've learned about averages since 5th grade or something. 6th grade, maybe. I don't know for sure. How do you find an arithmetic average? A mean. Add up the numbers and divide by how many there are. But this is more abstract. Here we're talking about the same idea, except with random variables based on a random sample. And again, when you say random sample, you're assuming they're independent, right? Because that makes all the theory a bunch easier. By the way, I didn't have time to think about an application of non-independent random variables over a triangular domain, except just in my mind before today. Before next Tuesday, I hope to actually write it out in Mathematica and show you some simulations, though we won't go through all the details, just to emphasize that they do have applications. So yeah, the sample mean is a natural or logical estimator for the population mean, as we've done many, many times. Here, I want to expand your mind here. Here's a new statistic, a new estimator that could also be used to estimate the population mean. Take the sample mean for a fixed n and add 1 over n. Of course, it's a weird thing to do, but it's something you could do. And if n is large, 1 over n is small, and so it's not that much different than x bar. Right? The x bar and x bar plus 1 over n will be close together when n is large. So if I wanted to, I could use that thing as an estimator for the population mean mu. Is it unbiased? First thing to do by hand here. Is it unbiased? Well, figure out its expected value. Thinking of n as fixed here. Expected value is a linear operator. I can write that. I know x bar is unbiased. An unbiased estimator for mu. Therefore, the expected value of x bar is mu. What about that one? What's the expected value of 1 over n? It's 1 over n. It's a constant. You might be scratching your head and saying, well, 1 over n is not really a random variable, so can I really take its expected value? Yes, you can think of constants as being constant random variables. They always take on the same value with probability 1. That's not equal to mu. Therefore, x bar is not unbiased. It's biased. It's a biased estimator for mu. That sounds bad. And yeah, it is bad, I guess. This would not be a good thing to do typically. But the point is, you could do it if you wanted to. Your boss might get upset at you, but you could do it if you want. You might get fired, but you could do it if you wanted to. Nobody's stopping you from doing it. Are there ever estimators that are biased that are still useful? Yes, there actually are. Question?
So is it that x bar plus 1 over n?
Oh, thank you. Yeah, typo. Sorry about that. I was getting so excited that I forgot my plus 1 over n. Yeah, don't do this if you value your job typically. But just for the sake of doing theory for fun, you could do it. And yes, sometimes we have to deal with estimators that are biased, maybe because there's just no clear alternative. We'll see an example, actually. We also know the sample variance is this and will ultimately be an unbiased estimator. I haven't gotten to the definition of unbiased and a new idea, the bias of an estimator. We're dividing by n minus 1, right? We've always talked about doing that because that makes this sample variance unbiased ultimately for the population variance. What is the population variance? If you think about populations in the old ways as being, say, all the people, and maybe if you're studying heights of people, all their heights, then you're saying, well, the population variance is really a similar kind of thing, except I divide by n instead of n minus 1, where n would be the population size, not the sample size. In reality, what we're really doing is we're thinking more theoretically. We're talking about the sample is coming from a population random variable from the distribution of some random variable x. And like I mentioned at the beginning, the population random variable it's got some variance that you'd compute this way. Assuming those moments exist, the first and second moment, which they don't always, right? So I am implicitly assuming these things exist. You can then take it square root to take have the sample standard deviation as an estimator for the population standard deviation. And here's an example. Here's our first example, simplest example, where we are using typically an estimator that's biased. S is biased for sigma, even though S squared is unbiased for sigma squared. Why? Well, it just still seems a natural thing to do. So why not? It's simplest. Could I possibly multiply this by a constant to make it unbiased? Yes, possibly. But that would be a complicating thing to do. So we don't typically do that. I could decide to divide by n instead of n minus 1. In fact, some statisticians do. Even for estimating the population variance. It results in a biased estimator, but some people do it anyway, just not most people. This textbook, well, our textbook here typically labels this sigma squared hat. This textbook labels it t squared, so I put them both in there. But t is not a t statistic. It's not a t distribution. Evidently, or maybe it's related. No, it's actually not a t statistic. We could do a sample median as an estimator for a population median. A sample median would be a middle value when you take your x1 through xn and list them out from lowest to greatest. If n is odd, there will be a middle value. If n is even, it will be the average of the two middle values. Sample median. A population median, at least in the continuous case, is just a number defined by that equation, which may or may not be easily computable. Right, where that capital F is the CDF. Does it make sense? You have thought about these things before. This has come up in homework before. In the context of a binomial random variable with parameters n and p, take the sample mean for the number of successes. You know, you think about me and free throws. I've mentioned this before. I'm a bad free throw shooter. When I play basketball, I can dribble okay, I can pass okay. I can't shoot. I just can't shoot. Okay. Even free throws when there's no pressure on the line. Most people should shoot at least 60 or 70%. I'm like a 40% free throw shooter. I've kept track of it. So maybe I shoot 10 free throws over and over and over again. The first 10, I make 3 of them. The second 10, I make 5 of them. The third 10, I make 4 of them. The fourth 10, I make 2 of them. A way to estimate the probability of success is to average those numbers, average those 2s, 3s, 4s, 5s, maybe sometimes 6s, to get an observed value of x bar, but that's not a probability estimate. I have to divide by 10 to get my probability estimate. Maybe x bar turns out to be 4.2. I divide by 10 to get 0.42. In the case where n is 1, this is kind of interesting. X bar times 1 minus x bar, you can check this out on your own, is an estimator for the variance of a binomial random variable when n is 1, sometimes called a point binomial. You're just doing one trial, you either have success or failure, x is either 0 or 1. You could use this as an estimator for that. N is 1, so that should make some sense. Okay, here's Here are estimators that come from the method of moments for a gamma distribution that, well, are biased. We talked about this example 3 or 4 weeks ago. I think it was that long ago because of spring break. It's in the book, talking about the method of moments. It's this example. Let's quickly recall the method of moments. You got a random sample from a gamma distribution with parameters alpha and beta. Looking up in the table for a gamma, the mean of a gamma is alpha times beta, and the variance is alpha times beta squared. Variance also does equal this, as you know. So in other words, these equations are true. Remember what the goal is. The goal is to sort of rewrite these equations in an alternate form to solve for estimators for alpha and beta. Replace each alpha with alpha hat, replace each beta with beta hat, replace these moments with these moments. There are conceptual differences here. These are equations relating numbers. Expected value of x is a number. The expected value of x squared is a number. Alpha and beta are numbers. The corresponding equations down here are not equalities of numbers. They're equalities of random variables, really. Estimators, alpha hat and beta hat, are random variables. They are statistics. Statistics are random variables. M1 and M2 are statistics. M1 is x bar, in fact. M2 is that thing. They're functions of the random sample. They are random variables. Algebraically solve for alpha hat and beta hat, you get this thing, these things, which is what I have in the Mathematica notebook. I also wrote these things in terms of t squared, where t squared was this thing up here. You're trusting me that I can do that. How would I know these are unbiased? I could try to take their expected values and see for alpha hat, for example, that I don't get alpha. However, doing the expected value of this, it's not clear what to do because it's ratios. There's no simple formula for the expected value of a ratio. So I'm to tell you the truth, seems like a hard thing to me to show or confirm that this is a biased estimator. However, we can do simulations to see that it seems like it's probably biased. Not going to worry about explaining these details. But essentially, this is simulating a gamma distribution with alpha equal to 3 and beta equal to 4. And I'm trying to look at what alpha hat and beta hat's observed values are. Doing this over and over, it's not clear for sure whether these things are biased or unbiased, and it's no proof for sure. If you make a histogram of the alpha hat values, you get one like that. Just looking at this particular histogram, it does seem like probably because the mass, most of the mass of it is over here, that probably the observed value of alpha hat, or the mean of alpha hat, is bigger than 3 for this example. But there were some examples where it was less than 3 in what we just did before. Seems to me, in redoing the simulation each time here, that we're mostly going to get values of the mean of alpha hat to be bigger than 3 here, right? It seems like most of these have most of the mass bigger than 3. That's, if I do this over and over, and if I keep observing that, that's enough to convince me that most likely the expected value of alpha hat is bigger than 3 in this case. Sorry, my computer seems to be working overtime here. Maybe because of those simulations, maybe because of the video recording, it's getting kind of loud. Here are some facts that we mentioned 2 or 3 weeks ago. For fixed theta bigger than 0, remember this, 2 times x bar, 2 times the mean, is a natural estimator for the right endpoint of a uniform distribution from 0 to theta. Remember that? At a uniform distribution from 0 to theta, pretend theta is 10, for example. You're going to get numbers in a random sample uniformly distributed between 0 and 10. Their average should be close to 5, half of 10. So if I double that, it should be close to 10. It's a natural estimator for the right endpoint. Another natural estimator is the maximum. We talked about that as well. Take all your data. What's the biggest one? If n is large enough, you got, say, thousands of data points, the largest one's going to be pretty close to 10. It's a natural estimator. I could do something strange like this as well. Multiply by n plus 1 over n. In fact, that's not a strange thing it turns out to do. It's going to be actually a good idea in a way I'll explain here in a few minutes. You can do simulation for this. I won't take the time. Let's go on to defining unbiased. We've already done that, but we also want to define something new, the bias of an estimator, sort of the measure of how biased it is the idea here. Theta has an estimator for theta. What's the bias of theta hat with respect to theta? It's the expected value of theta hat minus theta, which turns out by linearity to be the expected value of theta hat minus theta. Get the concepts right in your mind. Theta is a parameter. It's a number, a fixed number, but unknown. Its expected value will be itself. This is measuring the signed distance between the expected value of your estimator and the actual parameter itself. In the case of an unbiased estimator, the bias is 0. If the bias is positive, then theta hat will tend to overestimate theta over many, many samples. And if the bias is negative, then theta hat will tend to underestimate theta. As I've already said, the sample mean is an unbiased estimator for mu. The mean of the mean is the mean, and I mean it. Right? Expected value is a theoretical mean. X bar is also, well, it's an expectation of a random variable. X bar is a statistic, a mean. Mu is the population mean. This is going to make a histogram of X bar, histogram of X bar, many values of X bar, in fact, which are means from an exponential distribution with parameter 0.1 there. That's the lambda. Beta would be 10. What am I doing here? I'm trying to confirm that if I make this histogram, it should be centered near 10. Of course, if I do the simulation over again, it looks different, but it's still centered near 10. Also looks normal. That's the central limit theorem. If I compute just the mean itself many, many times, it's typically very close to 10, sometimes less than it, sometimes greater than it. Not a proof that it's unbiased, but it's numerical evidence that it seems to be unbiased. I can do a similar kind of thing with the sample variance. Here I'm dividing by n-1. If you do variance in Mathematica, that is the sample variance. This should be centered near This is for a gamma distribution. Where alpha is 25 and beta is 1. Its mean is 25 alpha times beta. So I'm taking the variance of it here. What is its variance? Its variance is actually alpha times beta squared, which is also 25. I'm computing a bunch of values of s squared and essentially making a histogram of all those values. It's not centered on 25 because it's not a symmetric distribution, but because of the right skew here, it shouldn't be surprising that it should be centered near 25. Excuse me, the mean should be 25, close to 25. And if you compute a bunch of values for means, yes, they are all pretty close to 25. I'm taking the mean of a variance, expected value of s squared, and it equals sigma squared. You should remember the sample standard deviation, like I've already mentioned, is not an unbiased estimator for sigma. Actually, this is kind of enlightening. If you take the mean of a bunch of standard deviations in the simulation, it's hardly ever bigger than 5. It is less than 5, close to 4.88 typically. And because I've made this number big enough, it seems like we're never getting bigger than 5, even though 5 is the population standard deviation, square root of 25. This is not an unbiased estimator for sigma squared either. Let's go back to our uniform distribution. We saw 3 weeks ago that 2 times x bar was unbiased. Let's redo the proof of that. What's the expected value of 2 times x bar in the case of a uniform distribution? By linearity, that's 2 times the expected value of x bar. The expected value of x bar is always mu. But then that begs a question, what is mu for a uniform distribution? It's theta over 2. So this simplifies to theta, the right endpoint of the uniform distribution. You know, this is not necessarily super exciting, but hang with me here. It's good to remind yourself of these things that we've talked about in the past. Will I test you on them? Yeah, maybe it's true false questions, multiple choice questions. We also saw that the maximum is not an unbiased estimate. And I also mentioned that 10 minutes ago. In this case, I'm doing 2 times the mean. I'm trying to estimate the right endpoint, which I am assuming is 10 here. Your histograms are typically centered on 10, or at least close to 10. And you compute the mean in each case, you typically get very close to 10. That's for 2 times the mean. What about the maximum? Variable maximum. Make a histogram. It's not centered on 10. In fact, it's very left skewed. And you compute the mean in each case, and you never get close to 10. However, if I multiply the maximum by n plus 1 over n, what is n in this case? N is actually 10, because of this 10 here. It's not 1,000. If I multiply by 11 over 10 in this example, the histogram still looks left skewed. However, it's shifted to the right a bit, enough to make the mean close to 10. These numbers are all pretty close to 10. So by multiplying the maximum by n plus 1 over n, which in this example, when n is 10, is multiplying it by 11/10, 1.1, it's enough to make this an unbiased estimator. It's unbiased. So just because an estimator is biased doesn't mean you can't adjust it by multiplying by some constant to make it unbiased. New definition. Asymptotically unbiased estimators. Let x1 through xn be a random sample from the population of x. Let theta hat be an estimator for the parameter. Then theta hat will be an asymptotically unbiased estimator if the bias goes to 0 as n goes to infinity. Note, if theta hat is already unbiased, it will automatically be asymptotically unbiased because the bias b of theta hat will always be 0 no matter what n is. This funny statistic, x bar plus 1 over n, is biased, but it's asymptotically unbiased. Its expected value, which does not equal mu, still goes to mu as n goes to infinity. Does that mean we should use it? Probably not. It's just illustrating the definition here. By the way, I'm picking 1 over n here to be the thing to add to x bar. But I could have picked 1 over n squared or 1 over n cubed or 1 over n to the 4th. Or some other function that goes to 0 as n goes to infinity. And so what I'm trying to say is there's infinitely many estimators you can use for mu. Is x bar the only unbiased one? Truly unbiased? No, not necessarily. Not necessarily, at least. Going back to the uniform example, that's an unbiased estimator for the right endpoint. If you divide it by 2, it would be an unbiased estimator for mu. And it does not equal x bar. For a given random sample, x1 through xn, of observed values, this thing will not, even when you divide it by 2, will not typically equal x bar. You're computing it in a different way. The observed values will typically be different. However, on average, they'll still average out to 5 if theta is 10. Hard to pay attention? Logan walked out. Just because he was bored? I don't know. Maybe he had to be somewhere. Yeah, it might be hard to pay attention to this stuff, but it's important. Okay, so do your best. And it's good to see examples. All right, here are the most important definitions for today. Consistency and efficiency. Let's start with consistency. Consistent estimator. Same setup, x1 through xn is a random sample from the population of x. Theta hat's an estimator. We are going to assume it's unbiased to start with in this definition. That's what this textbook does. Could we come up with a similar definition if it's not unbiased? I won't get into details. I won't worry about it. We say it's a consistent estimator for theta if this equation is true. Yeah, that's not so pleasant. If you've had real analysis, looking at that should make you feel like this is real analysis. You see lots of these kind of inequalities in real analysis, although typically with a strict less than sign. You could use a strict less than sign here. It would be fine. This textbook doesn't, so I copied them. What are you saying here? By the way, I haven't mentioned this, but I hope it's clear. You don't see any n's in here, yet we are letting n go to infinity. the theta hats typically depend on n, right? X bar depends on n in its formula. The maximum of x1 through xn depends on n. S squared depends on n. These things do typically depend on n. We just don't typically write the explicit dependence on n in the notation. The absolute value of the difference of two quantities, two real quantities, is the distance between them on a number line. This probability statement is then asking for the probability that the distance between theta hat and theta is less than or equal to some given number epsilon. If you draw a number line, we don't typically know where theta is, but let's just pretend we do. Theta hat, well, is a random variable, not a number really, but then I can think about its observed values, which are numbers. Maybe some observed value of theta hat's right there. That distance is the same as the absolute value of theta hat minus theta, which, because of the absolute value signs, could also be written like that. The absolute value of the distance between two real quantities is the absolute value of the difference. And inside the absolute value signs, you can write it either direction. And for that distance to be less than or equal to some number epsilon, means that epsilon's longer than that distance. It's a bigger number than that distance, I should say. And that's going to mean that, for example, if you take theta and add epsilon and subtract epsilon, this distance is epsilon here, and this distance is epsilon here. To say that the absolute value of theta hat minus theta is less than or equal to epsilon, then means theta hat's somewhere between these two quantities. Could be here, could be there, could be here. Theta hat's somewhere in there. That's what this is saying. You could also switch around the roles of theta hat and theta. You could say an observed value of theta hat is there, and this is theta hat plus epsilon, that's theta hat minus epsilon, and then theta itself is somewhere in the interval. You can think of it either way. Anyway, the probability of that goes to 0 as the sample size goes to infinity, is what it means for theta hat to be consistent. The likelihood, imagine epsilon to be small, like 10 to the negative 3 or something. The probability that theta hat will take on a value within 10 to the negative 3 of theta gets less and less likely as n gets larger and larger. And more than that, that probability goes to 0. If you want to get real close to theta itself. You know what? This is a typo. Sorry about this. I think I got a typo here. Yeah. Bad typo, in fact. Goes to 1. Not 0. For any fixed epsilon, you want theta to say theta hat's consistent means it's good, right? No matter how small epsilon is, 10 to the negative 3, 10 to the negative 1,000,000, doesn't matter how small. If n is large enough, in all likelihood, the observed value of theta hat will be in the interval. if theta hat's consistent. I did a bad job with that. That was a bad mistake. I wasn't thinking clearly about concepts. I was just typing without thinking. And I made a mistake in my typing. Say it again. Even if epsilon's really small, really, really small, if n is large enough, theta hat will be close to theta within epsilon of theta, no matter how small epsilon is. No, the smaller epsilon is, the larger n needs to be. As far as proving an estimator is consistent, you don't actually have to compute this limit typically. It's good enough to compute this limit, which is easier. And that's the theorem. Proving the theorem is not super easy. It requires Chebyshev's inequality. Using the theorem is not too hard though, especially with X bar. X bar is a consistent estimator for mu. Why? Because its variance goes to zeros and goes to infinity. Using that theorem. Relative efficiency of estimators. And we are going to try to start an example by hand here after I talk about this. Once again, assume n is fixed. I've got a random sample from a population. Let theta 1 hat and theta 2 hat both be unbiased estimators for theta. So they're both unbiased. Which one is relatively more efficient? It's the one with the smaller variance. At least for that value of n. In theory, for a different value of n, the other one could be more efficient. So this is talking about for a fixed value of n. And the relative efficiency, we say it's relatively more efficient in that context, and the actual relative efficiency is defined to be this ratio. So, the smaller that ratio is, the closer to zero it is, the more relatively efficient theta 1 hat is compared to theta 2 hat. And then in the big scheme of things, the big idea is that means theta 1 hat is a better estimator than theta 2 hat. We'd prefer using theta 1 hat compared to theta 2 hat. Here's an example. Let x1 through xn be a random sample from a uniform distribution on the interval from 0 to theta. Let theta 1 hat be n plus 1 over n times the maximum, and theta 2 hat be 2 times x bar. Let's calculate the relative efficiency. If it's close to 0 for fixed n, that means this is really a better estimate. If it's close to 0 for all n, in fact, it doesn't matter what the sample size is. That means theta 1 hat is going to be, in general, better than theta 2 hat. Can I do this calculation in 14 minutes? And try. Use Mathematica for help. So I have to compute the variance of these estimators. I'm guessing the variance of theta 2 hat is easier because it depends on x bar. And I know the variance of x bar. Guessing that one's easier. Let's try it. So x again is uniform on 0 to theta. Theta 2 hat is what I'm thinking about. That's the 2 times x bar. We know expected value of theta 2 hat, we already showed, is theta itself. We do know it's unbiased. That was what I showed you back here. What's its variance? What's the variance of theta 2 hat? As always, it would be the second moment minus the square of the first moment. And I could try it that way, but I think it's probably easier to use the fact that theta 2 hat is 2 times x bar, and then use the fact that I know the variance of x bar. The variance of theta 2 hat is the variance of 2 times x bar, and by properties of variances, that's 2 squared times the variance of x bar, right? Take the constant out front, but square it. That's a property of variances. In other words, it's 4 times the variance of x bar. But what's the variance of x bar? The variance of x bar is sigma squared divided by n for any random variable that has a finite variance. But this is a special random variable. I should be able to simplify the variance. I do have the formula memorized, but most of you probably don't. So let's look it up in the table. Chapter 4. Uniform distribution is in there. There it is. There's the density when x is between a and b. There's its variance. B minus a quantity squared over 12. Kind of a weird variance to divide by 12. But that is the way it turns out. You can check by doing some integrals. That is the variance. The length of the interval squared divided by 12. What is the length of this interval? It's theta. So it's theta squared divided by 12. Simplifies here then to theta squared over 3n. So that's the variance of this estimator. 2 times x bar in this situation. It does go to 0 as n goes to infinity. That's nice. That means it's a consistent estimator. Theta 2 hat is consistent. But that's not our end goal in this problem. In this example, we're trying to figure out its relative efficiency compared to theta 1 hat. Theta 1 hat, the variance is going to be trickier. Variance of that. If I can figure out the variance of the maximum, then I can multiply by this thing squared to find the variance of theta 1 hat. But how do you find the variance of the maximum? We need to find its distribution. We need to find its PDF. It's not as hard as it sounds. We can use our old friend, the CDF method. For shorthand, let's let, say, W equal the maximum, x1 through xn. What's the CDF of W? Are we ever going to get away from the CDF method? Yeah, we don't use it with regression, but it's still useful right now. If the maximum of n numbers is less than or equal to W, that means all the numbers must be less than or equal to W. Right? Does that make sense? If the biggest of a list of numbers is less than or equal to 10, then all the numbers have to be less than or equal to 10, because if any one of them were bigger than 10, the maximum would be bigger than 10. So I got a bunch of ands here. Our old friend independence comes into play again. multiply all these probabilities. Begging a question, what are those probabilities? Use the fact that X is uniform on the interval from 0 to theta. Its PDF is 1 over theta. Its CDF is X over theta. Right? An integral in my head. Of course, it's 0 when X is less than 0 and 1 when X is greater than theta, but I'm not worrying about writing these as piecewise. So that's the function I use for each of these. Because X1, X2 through Xn all have the same distribution as X. They all have the same CDF. So I get a bunch of W over thetas. How many of them? N of them. That is the CDF of the maximum. What's its PDF? Take the derivative with respect to W. Get this. We're running low on time. I'm going to have Mathematica do some integrals for me. So the mean is the integral of W times the PDF. What should this equal? Not quite theta. Theta times n over 1 plus n. Oh, there we go. That's why I multiply by n plus 1 over n. Times the maximum to make it unbiased. Not done, I need the variance as well, so I need the second moment. Ignore this part, the if RE of n is greater than -1 or -2. That's Mathematica is wondering if I intend n to be a complex number or not. That's the second moment. So what's the variance? Second moment minus the square of the first moment. There's the second moment. Or excuse me, no, that's the variance, excuse me. That's the variance of the maximum. With Mathematica, we figured it out to be n theta squared divided by n plus 2 times n plus 1 quantity squared. So that was not the final variance I'm after, though. I'm after the variance of theta 1 hat. Theta 1 hat was n plus 1 divided by n times the maximum. Factor out the n plus 1 over n and square it. Get n plus 1 squared over n squared times the variance of the maximum. Oops, sorry. Variance of the maximum, which we've just found to be this thing. So plug that in here. The n plus one quantity, the n plus one's quantity squareds cancel. And one of the n's cancels. After cancellation, it looks like we are left with theta squared over n plus 2. Oh, no, n times n plus 2. One of the n's cancels. Now we're ready to calculate the relative efficiency. Take this variance and divide by that variance. The theta squareds cancel. The n's cancel, actually. This n cancels with this n. The relative efficiency, almost out of room and almost out of time, variance of theta 1 hat divided by the variance of theta 2 hat ends up equaling what? Theta squareds cancel, n cancels on the top. We end up with a 1/3 on the top after cancellation. And on the bottom, we end up with an n plus 2. So it looks like it's 1/3n plus 6 for the relative efficiency. What is it on top? I did it the other way around. I'm sorry. Okay, yeah, that's wrong. I mixed up theta 1 hat and theta 2 hat. Multiply the top and bottom by 3. It's 3/n plus 2. And that's going to be less than 1 if n is bigger than 1. So what's the punchline? The punchline is theta 1 hat's better than theta 2 hat. They're both unbiased, and one is more relatively efficient. Where did I put the paper word? Theta 1 hat and theta 2 hat. Theta 1 hat was n plus 1 over n times the maximum. Theta 2 hat was at 2 times x bar. N plus 1 over n times the maximum is better, is what this means. All right. Have a good day.